In this video, we are going to talk about models for fraud detection. Models in general can be divided into rule-based models and machine learning models. Rule-based models are usually based on a set of rules that you, the user, have specified with a level of confidence based on your past experience. And you think that this is relevant for fraud detection, therefore you pass this down to the model for it to determine potential fraudulent transactions. And it gives you this collection of potential fraud transactions, and you may do some downstream analysis to see whether each of the transactions on this report are actually fraudulent or not. The problem with this kind of model is that it's dependent on your past experience, which are prone to bias and other personal opinions that you may think are relevant to fraud detection, which may not be. And another problem is that it's too static because it's based on one overarching set of rules that you have summarized based on your experience, and it may not be relevant to the present time given the pace of change in the financial crime world. Therefore, on the flip side, we have these machine learning models, which gives the machine a chance to learn up patterns based on an input dataset that you provide it with. And in running this model, it applies this pattern on a new dataset that you're looking to predict fraud with, and it will output a list of transactions that it thinks are fraudulent. And you can actually calculate an accuracy score in your model so that you can have a quantifiable metric on how the model is working. So let's have a deeper dive into the kinds of machine learning models that are out there. So these are the most frequently used models out there, and we are actually going through the decision tree model today as an example, just to give you an overall idea of how these kinds of models work. But let's have a look at how each of these work in the background and when to use them. So the decision tree model formulates a series of questions that test on an attribute, with each descending branch corresponding to one possible value for the attribute. And it's usually used with nonlinear datasets, numeric and categorical data, and data with missing attributes. And the next one is the k-nearest neighbors model, and it uses the number of a data point's nearest neighbors to predict which group it should belong to. And it's usually used with smaller data sets because of the computing power associated with determining the nearest neighbors of a data point. It can compound tremendously as the data set grows larger. And the next one is the logistic regression model, and it uses the logistic function to predict a binary outcome based on a set of independent variables. And it's usually used with dependent variables that are categorical and binary. And the next one is the support vector machine model. And it tries to find a line in multidimensional space between classes of data and class new data points on if it lies on the positive or the negative side of the line. And it can learn from a limited number of samples. So for our decision tree model example today, to save on the complexity of the example, I have limited to 1,000 lines of data. And when you're running that kind of data with other models, it may not learn up any pattern from the data, but with the support vector machine, it's no problem. And it can work better on smaller data sets due to training time. And the random forest tree is a collection of decision trees whose results are aggregated into one result. So the decision tree model can grow very comprehensive, but in the end, it's only one tree. So it's still limited in some respects. But what if we combine a forest of those trees together? Just imagine the predictive power that the random forest would have by combining all of these decision trees. But one problem with this is that it can be very hard to interpret with the human brain at that point because it's overwhelmingly complex. So if that's not a problem and the data sets are larger compared to others, then you might consider the random tree model to use for your data set. And last but not least, the extreme gradient boosting model combines the linear model solver and the tree learning algorithms. And this is usually used with small and medium data sets with subgroups and structured data with few features. So now that we have a general understanding of the different types of models that are associated with machine learning, we are ready to jump into an example with the decision tree model. And the dataset that we're going to be using for this model run is contained in the payment data CSV file. So before we are able to do anything, we're going to have to import this dataset into our code book. So to do that, we're going to need the help of pandas. So we're going to have to say import pandas as PD. And we're going to use this shorthand PD from this point on to reference the pandas package when we want to use it in this codebook. And so to import this CSV file into our code, we want to say data is equal to pd.read CSV and in brackets payment data.csv, and we want to just call this data set name called data, and it will give you a preview of this data set. And we can see that it's about 1,000 lines, so it's not a large data set to work with. So the output of the model should be easy to interpret. But before we go on any further, I would just like to quickly check if there's any null values in this dataset. So the way I do that is to say print data.isNull open and close brackets .sum open and close brackets. And if I run that, I can see that there is none. So that is good news. So we can proceed to the next step. So before I jump into any dataset, I would just like to do a high-level visualization to see the structure of the dataset that I will be working with. So in this case, a quick and dirty way to see the structure of this dataset is to count how many transactions are within each transaction type within this dataset. So I would just like to put a name to the value count of each transaction type within the type column of the dataset. So I'm saying type is equal to data with the column named type dot value underscore counts. And once I have done this, I can use this parameter that I have defined and separate out the name of the transactions and the count values of each transaction. So for the name, I would like to name it as transactions, and you can see how I have referenced this as the name in my plotting function, and the count values of those transactions is named quantity. So quantity is being used as the value in my plotting function. So before I get to the plotting function, I will need to import in the Plotly Express package as px and call this up in my plotting code and say px.pie because I'm trying to plot a pie chart. And in brackets, let's specify the data source for this function, which is data, and values is equal to the quantity that I have defined here. And the name is equal to the transactions that I have defined above. And the hole is just the hole in the middle. So you can adjust this to be larger, or you can say, I don't want any. That's up to you. And last but not least, I would like to just give it a title and say figure show. So that will show the figure that I have defined in this line. There. So that is a high-level overview of this data set. And once I have this in hand, I would be ready to prepare for my machine learning model. In order to prepare for our upcoming model, it's ideal that we convert any input columns into numerical data so that our model can more easily pick up patterns from those columns. And we want to convert any columns on the output side of the model into text data so that the users would more easily read and interpret the output of the model. So in our case, the type column started out as text-based. So we would want to convert the data that's contained in this column into numerical data. So the way we do that is to say data square brackets type. So that's the type column within the data set. And we want to say map, and in brackets, cash out is converted to ones, payment converted to twos, and cash ins converted to threes, transfers converted to fours, and debits converted to fives. And on the output side, our is fraud column started out as binary, so zeros and ones. So imagine a user having an output that's 0. He or she would have a hard time interpreting what that means. So we would want to convert the zeros and the ones into no fraud and fraud. And to preview what we have done here with our mapping, we can just say print and in brackets data.head open and close brackets. That way, our type column is converted to numerical data, and is fraud column converted to text-based data. And we can't do any type of model without defining the X and the Y of the model. And to do that, we would need the help of the NumPy package. And so we would need to import that in as NP. And we can call that in our functions. And for X, we want to say X is equal to np.array, and in brackets, we want to call in the type column, amount column, old balance column, and new balance column from the data set. And similarly for Y, we want to say np.array, and in brackets, the data set, and this time we are interested in the isFraud column in this data set. And once we have defined the X and the Y, we are ready to do what is called the training versus testing data split. So we are trying to basically divide this data set into training and testing components. And the way we do that is with the help of the train test split function from the sklearn model selection package. So sklearn stands for scikit-learn, and that is the machine learning package within Python. So for this particular purpose, we want to say from sklearn.model_selection import this train test split function, which we will reference down below in our code. And to specifically carry out the split, we want to say xtrain, comma, xtest, comma, ytrain, and comma, and ytest is equal to train test split, and we want to reference the X and the Y that we have specified above. And we want to say the test size is equal to 0.1. And 0.1 just means 10% of the population data set. And we want to give this a random state number. So the random state number is literally a batch number that you have specified for this cohort of data set, if you will, so that you're not dealing with a different subset of the data each time you execute the model. So there is some predictability in between your runs of your data. And this can be any number, and usually it's defaulted to 42 just because in the statistics field, this is supposed to stand for the number that solves the grand question of the universe, so people say. So you can literally put any number here just to make sure that it's consistent between your executions. And next, we are ready to call in our decision tree model. And to do that, we will need to say from sklearn import tree. And we will reference this tree in our code below, where we say model is equal to tree.decision_tree classifier, open and close brackets. And once we have this model imported and defined, we would be ready to fit this model into our xtrain and ytrain axes that we have defined above in this line here. So we would like to say model is equal to model.fit, and in brackets we want to reference the X train and the Y train. And so at this point, the model is formulated. But if you want to see how it looks like, you can easily just say tree dot plot underscore tree, and in brackets reference the model, this model that you have defined. And for my purpose, I just put in field is equal to true so that I can see which node is actually having the fraud output. So we can easily see here, those are the fraud outputs that are, embedded in the model that's being visualized. So this is basically the tree that we will use to determine whether a transaction is fraudulent or not. And if we blow this up, it would look something like this. And if we go back to the X definition that we wrote above, we will realize that the model has converted these 4 variables into x0, x1, and x2 here, and x3. So x0 is type, x1 is amount, x2 is old balance, x3 is new balance. And you can see that the machine has automatically picked values in these variables that makes the model most efficient to create an output to determine whether a transaction is fraud or not in the most time efficient manner. So it has determined that it's most efficient to start with the amount. Okay, so x1, it says, is most telling if we create a node at 212. So anything less than or equal to this value will go to this node. And anything that's not will go here. And it will create these downstream branches so that we can arrive at these resulting nodes that will tell us whether a transaction is fraudulent or not. And these are automatically created without you doing anything, even though you provided the input data set for it to work with. And you can see here that it has dropped x0 because it has determined that x1 and x2 and x3 are most telling to determine whether a transaction is fraudulent or not. So it's not so much that the transaction type is a determinant in deciding whether a transaction would be fraudulent. It's more the amount and the balances. So therefore, it has excluded x0 from the model. So you can throw in any variable that you feel is relevant for fraud detection in here, but the model may pick and choose which ones it will actually use. So once we have formulated our model, we are ready to output an accuracy score for it. And because we only have 1,000 lines of data, the accuracy score is only 2 decimal places. But if we increase the data size that we input into our model, this accuracy score will have many decimal places, so that you know the accuracy is increasing with the input data size being increased. So to output an accuracy score, we can simply say print model.score and in brackets reference the X test and the Y test, so that you will have a score that's telling you that it's accurate 99% of the time. And having one accuracy score like that is satisfactory, but it's not sufficient because it's only one score. So you might want to do a cross-validation so that you are taking an average of different runs of the accuracy estimate. So the way the cross-validation works is that it divides this data set into several components, and say 5 in this case. So 4 of them may serve as the training data set, and one subcomponent will serve as the testing data set. And between each run, each component will take turn being the testing data set. And so in the end, instead of one accuracy score, you will end up with 5, so that you can take an average of those accuracy scores and taking a middle ground between the 5 scores, so that you will end up with a more unbiased score and a more accurate estimate of the actual accuracy of your model. In order to run a cross-validation, we would need the help of the cross-val score component of the sklearn model selection package. So we would need to say from sklearn model selection, import cross-val score, and in order to run the cross-validation, we need to say cross-val score and in brackets model, which is the model that we have used for our single accuracy score, and which is defined here as well. So once we have defined the model, we want to reference the X test and the Y test. And we can specify the number of components that we want to divide our data into. So here I have left it as 5, but you can increase or decrease according to the need of your data. So once you are satisfied with an accuracy score, and these will be different as you are working with a larger data set. So the end average of these 5 scores will be some kind of midpoint that will be different from when you're running a single accuracy score here. So once you are satisfied with the average of these scores, you would be ready to run some predictions with your model. So you can run it on a single transaction with these features. So this particular transaction is a transfer with the amount being 9,000.6, and the old balance is also 9,000.6, and the new balance is 9.86. And I want to pass these features down into a variable name named features, and the way we do that is through the help of the NumPy package and we want to define that in an array. So once we pass this into our model by saying print model dot predict and in brackets features, which is these features here, it will tell us whether this transaction is fraudulent or not. So now it's telling us that it's not. But what if I start changing things in here? What if I run it like that? Now, that is a problematic transaction because these just don't add up. So once you have had a chance to change things around in here, at some point you will trigger a node in this decision tree that makes the result fraudulent. Now, that's how you do it with one single transaction. Now, what if you want to do it on a batch of transactions? First, you would want to define a data frame for your X-test dataset. And the way you do that is through the help of the pandas package. And you want to say pandas.dataframe and in brackets X-test. And you want to give it a name called X-test underscore df. And df stands for data frame. And the data frame is just rows and columns in a table in Python. So once you have defined a data frame for your X-test, you are ready to pass it into this feature, which used to stand for only one transaction. Now it's holding a whole bunch of transactions. And if you use the same prediction function that we have used before for this one single transaction on this feature, which is now equal to the whole entire X-test dataset, you can see the result of all of these different transactions, and you can see that there's one fraudulent transaction in there. So we have this result, but this is not telling us anything useful because it's just a concatenated batch of results. So we would need to put this into a meaningful way so that it tells us what these are referencing. So the way you do that is to first convert this into a data frame so that we can do something with it. And the way we do that is, again, through the help of the pandas data frame and say pandas dot data frame and in brackets predict, which is this array here. And once you have it into a data frame, you are ready to concatenate it with the X-test data frame that we have defined here. So we want to say concat, which is the name of the concatenated data frame, is equal to pandas.concat and in brackets X-test df, comma predict df, and axis is equal to 1. So axis, when it's equal to 1, Python knows that we are working with columns. And the way we have ordered this is telling Python that we want to put the predict df after the X-test df. So at this point, we have technically formed our concatenated data frame. So there. But the only problem with this is that the column headers are not very helpful in telling us what the column is actually referencing. So we want to reset the column headers of this data frame that we have here. So we want to say concat.set axis, and axis is equal to 1, so that Python knows that we are working with column headers instead of row headers. And we want to just list out the column headers that we want to show in this data frame. So in order from left to right, the first column is the type, second is the amount, third is the old balance and new balance, and then the last one is fraud and with a question mark, so that we know that this last column is telling us whether the transactions featured in the previous 4 columns is fraudulent or not. So if we run this, there we have our ending result data frame that is telling us the testing result of our model for each line of transaction that's contained in this data frame. So I hope that is helpful. This is how you would run fraud detection through a machine learning model. And I hope that you can use this in your fraud detection tasks. And hopefully this will help you do some meaningful detection. I'll see you next time. Bye.